Okay, so when we left off in the last video, we were talking about the different kinds of water contamination. And we basically said that there are three different kinds, right? There are pathogenic microorganisms, and inorganic chemicals, and organic chemicals. And what we need to keep in mind is that not so much with pathogenic microorganisms, but particularly with inorganic chemicals. These would be things like metals, for example, which we'll come to in just a second. The reality is that these are very, very widely spread, and you can also make the case it's true with organic chemicals as well in the modern environment. The real question is, how much of these things do you have to be exposed to in order for there to be a problem? And so, as you may recall, we operate using guidelines which include MCLs, which are the maximum contaminant level. And maximum contaminant levels are calculated based on a couple of different considerations. One is our ability to detect this contaminant, obviously. Our ability to detect the contaminant. Another is its potential health risk. And the third is its potential to be in drinking water. So all those considerations go into defining maximum contaminant levels, and I'll give you a list of some of those coming up. So let's talk a little bit about pathogenic microorganisms. So these pathogenic microorganisms include pathogens, things that you've probably all heard of, things like typhoid or cholera, polio, hepatitis, dysentery, and these are obviously enormously important. Lots of people are impacted by these globally, although despite massive efforts to try to rein them in. And one of the things that I think is particularly fascinating is that dysentery, which leads to diarrhea, is one of the great killers of people around the world every year, particularly the young. Dysentery leads to diarrhea, which leads to dehydration. And approximately 400 children alone per hour globally die from dehydration and other symptoms or other effects associated with dysentery and other waterborne diseases. And these can be treated. The water itself drinking water can be disinfected through a variety of mechanisms. So treatment, disinfection. So one way is to use a chemical disinfectant to sterilize the water before it's ingested. And so here in the United States, the most common is chlorine. Chlorine is added to the water. It's a very strong oxidizing agent, and so it kills the viruses and bacteria that are present. You can also use iodine, although chlorine is by far much more common. Alternatively, another up-and-coming mechanism, and this is being used actually new Iowa City wastewater treatment plant is UV, ultraviolet light. Ultraviolet light. So instead of adding chlorine to the drinking water, the water passes in a thin film around a bunch of very, very strong ultraviolet lights. And the ultraviolet lights don't actually kill the microorganisms, but they do fracture their DNA, making it impossible for them to replicate. So they become essentially sterile, and without the ability to replicate, they're harmless. One of the nice things about ultraviolet light, as opposed to chlorine, is that chlorine itself is very, very dangerous, particularly when it's concentrated. So if a concentrated amount of chlorine gas were to be released, wherever that plume went, it could hurt or kill a lot of people. Ultraviolet light, obviously, is just that. It's just ultraviolet light. When the power goes off, the impact of it ends. Of course, if power does go off, then this means of sterilization is eliminated. The nice thing about chlorine is it's a chemical reagent, so you can just keep adding it to water, even if the power has gone out, and you'll still continue the disinfection. All right. In terms of inorganic chemicals, what we're thinking about here are the atoms and the molecules that are non-organic. So organic would mean right they're made of the hydrogen, carbon, oxygen, that sort of thing. So these are all the other components. So, for example, in places like in some mining areas, we often have to worry about metals in water. And metals can include things like arsenic or lead, those sorts of things, or mercury. Each of which has its own, they have their own solubilities and their own impacts on human health. So therefore they have different MCLs. Places where you'd expect to get things like a lot of arsenic are in areas with a lot of tin mining. Tin mines are often associated, tin is often associated with arsenic. And it can be present in very small concentrations, arsenic can, but even very, very small concentrations can be quite damaging. The MCL for arsenic has actually been something that's been fought over a good deal lately, because mining companies want to see it reduced want to see the MCL raised as far as possible, and the science isn't settled, and so it's what is generally recognized is that you want to have as little arsenic in your drinking water as possible, but defining that exact boundary has been difficult. Lead is associated with minerals like galena. If you've ever heard of Galena, Illinois, or Galena, Kansas, galena is a mineral, PBS, lead sulfide, and in areas where lead is mined a lot and a lot of the rocks are exposed on the Earth's surface, the sulfur oxidizes, and the way it did, as we talked about with acid mine drainage, and that creates more acidic solutions, which then carry the lead along and can get into drinking water, including rivers and streams. Because of the relationship between pH, and just a quick primer, if you haven't seen this before, pH is the negative log of the hydrogen ion concentration in water, and all that means basically is that as you go 7 is considered neutral. As you go down closer to 3 and 1 and so forth, you are increasing the amount of hydrogen ions in solution and therefore making it more acidic. And as you move this way to 9 and 12 and 14 and so forth, you are decreasing the hydrogen ion concentrations, therefore you're making it less acidic. It's a little bit weird. It has to do with the fact that this is a log scale and the fact that it's negative. But anyway, so what happens then is that because pH or acidity plays such a big role, plays such an important role in the solubility of metals like lead and arsenic in water, then the things that control the pH of the water are also really important. And it's not just this oxidation of sulfur, it's the kind of rocks that the streams and rivers are flowing through. The rocks hosting the mine or the stream also impact water pH. For example, in the Rockies, in the Rocky Mountains, for example, in the Rocky Mountains, there's a lot of granite. A lot of gold mines are in granite. And granite is composed of minerals which are based on silica. They're all derived from silica, which is silicon and oxygen. SiO4 is what silica is as a molecule. You don't have to know a lot about this, other than these are the most abundant kinds of rocks on Earth. So there are lots and lots of rocks like granite that are made of silicon and oxygen. Well, silicon and oxygen-rich rocks are not very chemically reactive. They're not soluble. Those minerals are not very soluble in water. So when water flows across a granite, not a whole lot happens to it, it being the water or the rock. However, in places like the Midwest, we have lots of sedimentary rocks, including lots of limestone. Limestone, I think we talked about this before, is calcium carbonate. And when calcium carbonate reacts with an acid, or an acidic solution like a acid mine drainage or something, what happens is that the calcium carbonate is very reactive, very reactive. It dissolves easily in the presence of acid, and as a result, it neutralizes the acidity in the solution. So what does this mean? This means that if you have a mine in a place like Missouri or Illinois that was formed in limestone, so people were digging through the limestone in order to pull out the galena or the sphalerite, which is a zinc mineral, right? You wouldn't want lead or zinc in your drinking water. So you've got these two minerals, galena, PBS, lead sulfide, and you've got sphalerite, which is another mineral that's often associated with galena, which is zinc sulfide, right? And you have a big open pit mine that's been dug in order to get out all of the galena and the sphalerite, and the tailings, the leftover crushed rock that's left over, have been thrown up into these huge piles across the land surface, right? Well, in these tailings are little bits of galena and sphalerite as well as pyrite, and they are all reacting with oxygen and water in the air and the rain and making acidic drainage, right? acid mine drainage. Well, if that water was free to just flow across the land surface in streams, you would expect to have not only lots of iron from the pyrite, but lots of lead and lots of zinc from the little bits of galena and sphalerite that are in here in the water, which would be an enormous problem. Luckily, however, a lot of the rocks in the Midwest are limestone, and so whatever acidity is produced in this acid drainage is very, very quickly neutralized by interaction of these acidic waters with limestone. So the pH, which was very, very low, very acidic, very quickly gets brought up into the neutral range by interacting with the limestone. And as a result, the lead and the zinc and the iron, which would otherwise be floating and dissolved in the water, get precipitated onto the stream bed and stay there. And so they're not mobilized. So neutralization of pH by limestone minimizes the solubility of dangerous metals from these mines. So that's all well and good, right? But the question is, what do you do in areas where you don't have limestone? What do you do about that? And including in places like the Rocky Mountains. And what's done is to bring the limestone in. So you have an old mine shaft here on the side of a mountain. This is supposed to be, there's a tree out in front of a mountain, and there's this big mountain here. And here's an old mine shaft that's been dug horizontally into some mountain, and water is constantly seeping out of it. And the water has a very low pH and is very dangerous and colored red colored due to the high amounts of iron that are in it. And why is there so much iron? Because the pH is low, right? Iron is very soluble in water. This is a stream. So this is acid mine drainage. And when this stuff trickles down to a bigger stream that happens to be running along down here with lots of fish and stuff in it, it'll start to decimate the ecosystems of everything down here. So this will look pristine, and this will be decimated by the acid mine drainage. So what do you do? So what people have done, not people, usually the federal government, or in some cases mining companies that have been held responsible for this, is they come in and they build a big retaining wall and essentially a large dam and a huge reservoir, and they, as big a reservoir as they can, and they try to impound the water here in this reservoir, the water that's leaking out of the mine. And now, just obviously, if you put the water in there, eventually it's going to spill over the top and go right back down to the stream. So what they do is they add into that big blocks of limestone. And what you hope, of course, is that this limestone is going to be sufficient to neutralize the acidity of the water coming out of here. So you'll get very low pH coming in and more moderate pH coming out. Because the pH has been raised, because the water is no longer so acidic by the time it's entering the stream, it's also no longer carrying so many metals. So the water isn't as poisoned by the metals. It's not as poisoned by the shock of this low pH water, and therefore the streams are able to recover. This works generally pretty well for short periods of time, but one of the problems, of course, is that when you look closely, if we just kind of zoom in here, you have a big block of limestone in there, and this acidic water coming in carrying lots of iron. Right. Well, as soon as that water begins to, the pH of the water begins to climb, the iron that was dissolved in this acidic solution begins to flocculate out, begins to settle out. And so you get iron coating everything here. The iron is going to settle out and cover these rocks. And as it does, it's going to form essentially a barrier to continued chemical reactions. Continued chemical reactions, right? So the more you cover these limestones with iron that's settled out of the water, the harder it is for new acidic water to be able to react with the limestone to get neutralized. So these sorts of systems require lots and lots of work. In general, it's better to put lots and lots of small pieces of rock in there, and then you can sort of stir them up once in a while. But it's not easy, and it's a never-ending problem, right? Because there is an infinite amount of water capable of soaking through these mountains, and essentially an infinite amount of oxygen and pyrite back in there that are going to keep supplying these things. So this is a fix, but it's not a long-term solution. Okay, what else? Is there anything else before I'll stop there for now.